Okay. Hello, everybody. Welcome to the Latin American webinar of physics. Today we have a double celebration because Carla Bonifaci, she's our new coordinator, and also she's gonna be the new host of today's webinar. Carla, welcome to lawphysics, and you can continue.
Okay, hello everybody. So I'm very happy to be here and to present today Xavier Bertou. He will talk about dark matter experiment named DAMIC, and he will show the recent results. So Xavier, thanks for accepting to be here. Xavier now is in France, so he's a research director at IJCLab. And he's working on direct dark matter group. He's leading the group. He was working before in Argentina. He spent more than 20 years at the Centro Atómico Bariloche, where we have the opportunity to work together. And he's an expert on astroparticle physics, and he did in the past a lot of contribution in cosmic rays, and now he moved more to the dark matter research. So thanks a lot for being here. The floor is with you, if you want to share.
Thank you, Carla. Thank you, everybody. Thanks for the invitation. So it's my pleasure to tell you about my current research topic. And oops. I will discuss on the physics and on the detector side, because the physics we are doing is really great. I hope to convince you about that. And it's being done because we have a great detector. So I will have some a significant part of the talk on the detector itself. So dark matter and the single electron. So that's first part of my presentation. So what is dark matter? I think everybody here knows. We have a lot of indications in observations of the universe that there is an extra matter in addition to the visible matter. If we look at galaxies, the way they rotate, we see that the stars away from the center of the galaxy are moving too fast. They should move away. The galaxy should not exist. Yet here they are. We see here you have examples of gravitational lensing, the CMB, so the cosmic microwave background, light from the Big Bang, from the first moment when light decoupled and was able to travel after the Big Bang in the universe. And also this is a bullet cluster, so collision of a group of galaxies. And when we look at all these phenomena, we always have to add more matter than the one we see. And it's always more or less the same amount of matter. So something like 6 times more of this dark matter than the visible matter. So all these indications lead us to believe that there is an extra dark matter. There is a huge mass range for this dark matter. So this is a drawing from XKCD with some true candidates inside, and some more funny ones. This is the scientific version of the previous plot. It's not as funny as the other one. But still, you see it goes from ZeV to solar masses, so multiple of solar masses. So it's a huge energy range, and there are a lot of candidates. Usually, you have 2 ways to create dark matter after the Big Bang. Either you have dark matter in equilibrium with standard model particles, and then you manage to get to the right density we have today through what is called the freeze-out mechanism, in which when the universe becomes colder, then you cannot create any more dark matter. So what was in thermal equilibrium becomes a one-way process where you only have a disintegration of dark matter particles, interaction, self-interaction, and creation of standard model particles. And then at some point, the universe starts to move too fast to have this process efficient. And so this diminution of the amount of dark matter freezes, and this is what is called a freeze-out. Then you have another way to create dark matter is to consider that after the Big Bang, you don't have dark matter after the inflation. And then slowly you create dark matter out of interaction from standard matter. So this is what is called the freezing. So here the cross-section has to be very low, and it has to have a precise value so that you get the right amount of dark matter as of today. So these two phenomena, freeze in and freeze out, have been here for a while. And you have three ways to look for dark matter. Either a collider search, so you collide two normal particles and try to create dark matter. Indirect detection, you look at the universe and try to see two dark matter particles annihilating into photons, for example. Or direct detection, which is what I'm going to discuss, which is you wait for a dark matter to hit one of your detectors and to leave you a visible signal. For that, you have to go underground just because there are cosmic rays. And right now we are all in a bath of cosmic rays, something like 100 per square meter per second. So 100 particles go through us every second. And so if we build a detector, then we are going to see these cosmic rays and not dark matter, which interacts very weakly since it is dark. And so we have to go deep underground, and here are some names of underground laboratory, and as a function of the depth, which is in water equivalent. So it's something like 2,000 meters for the deepest one here on this plot, which is Sudbury in Canada. And the muon background, which is the most penetrating of these cosmic particles, goes from 100 per second at the level of the ground up to 1 every day when you go in the deepest laboratory. So this is what opens the window to see dark matter. So then once you're underground, then you build a huge detector. So this is Xenon in Gran Sasso in Italy. You can see this is a building, right? These are 3 floors, so it's a really huge detector. And then you wait for a dark matter particle to interact in that. This is the particle you're looking for usually is a WIMP, so that's a weakly interactive massive particle, just because if you take the freeze out, I talked before, and you consider, it depends on 2 parameters, basically, so the mass of your particle and the cross-section of your particle. So if you consider the mass to be the weak scale mass, so let's say 100 GeV, and then the cross-section to be the weak scale, cross-section, then you get exactly the amount of energy density that you expect for dark matter. So this is what was called the WIMP miracle. And so there are a lot of experiments which are trying to look for it. And so in these plots, typically what you have is a WIMP nucleus cross-section, so probability basically of a WIMP of impacting a target in your detector as a function of the WIMP mass. And so 100 GeV, weak cross-section is something like that. And the problem is all these lines are experiments which have not seen anything, and are therefore saying that above this line, dark matter cannot exist. If it were there, they would have seen a lot of them, and they didn't. So basically, the WIMP right now is kind of dead. I mean, it's you can always modify the theories to get in the still available region, but it's no more this very natural WIMP miracle we had before. So then we go to other theories, and the dark sector is a very, very simple theory where you just add a new symmetry with a dark sector, U1. So the simplest, you can see that as a dark electromagnetism in some sense, so a dark photon. You get some coupling with a standard photon, and you can again create dark matter through freeze out or freeze in different mechanisms. Here, since it mixes with electromagnetisms, then you will have interactions with the electron. And so you expect to be able to observe an electron recoil. And it's also a different energy scale, typically from the MEV instead of the GeV we had for the nuclear recoil. And so this is the main difference. So up to now, most of the experiments have worked in the nuclear recoil, so looking for WIMPs. GeV to TeV, you get a nuclear recoil as a signal. Signals are in the TeV range, so that's a lot of electron volts. But some detectors lowering their analysis and not looking at all the signals they were supposed to look can get up to let's say 20 electron volts. Now, if you go to an electron recoil, then you are looking for the dark sector, so MeV to GeV dark matter particle that couple to the electron. Deposited energies are the electron volt range, so that's much lower than this. And what is nice is that this is exactly the band gap we have for silicon, and so this is something which rings a bell for an experimentalist. Silicon is we have a lot of silicon detectors everywhere in particle physics. So let's have a look at a silicon detector, in particular at a CCD. A CCD is something which was invented more than 50 years ago, and which was initially thought as a memory. So here you have a picture of it, and basically the idea is you would inject some charge, and then you would move it into the memory, and you could read it later. So it was a way to keep some charge into memory. But very fast, people understood that this way of moving charge could also be used to take images and to build digital camera. And so now there are a lot of CCDs. It was Nobel Prize. And you've probably seen in the last few days a lot of images from LSST, Vera Rubin telescope, so the largest camera on Earth, 3.2 gigapixels. And well, all these squares here are one of these CCDs. Now, how does a CCD work? Well, so here you have a pixel, and each pixel is composed by 3 gates. And to each of them, we are going to put a specific voltage, which can be either high or low. So if you have high here, and low here, then you are going to get a potential well. So this was a drawing of mine, you can see. And then here you will again get a 1 and a 0 and a 1. So you will have again the same potential well. And this is a better drawing of this potential well. So you have the first phase, which is high, then a second phase, which is high, and then the central phase, which is low. And so you get this potential well, which is where you are going to accumulate charge in the pixels. And so you expose your camera to take a picture, and then you close the shutter. And so you got a lot of photons entering in each pixel, doing photoelectric effect. And so you will have a lot of electrons here. You accumulate them in the potential well. And so you have a lot of pixels, a lot of light here, for example, and not a lot of light which hits this pixel. So you have less charge here. Now, the game is to try to read this signal. So if you think of what you have in your pocket, your cell phone does not work this way. Your cell phone is a CMOS, and so every pixel is read at the same time in parallel. So it's very nice to make videos, but it's more complex. You have to have electronics for each pixel, and so it's usually not as precise as a CCD. So that's why in astronomy people still use CCD, even if you are going to see it's much longer to read a CCD. So to read a CCD, we have to move the pixel charge up to where we are going to read them. So for that, we are going to lower this node, which will lower this voltage and this voltage. And here it is. And so the charge which was in that pixel now is moving among these 2 gates. And then we are going to raise the central gate. And the charge which was in the middle of the pixel, after this operation, has moved by 1/3 of a pixel. And the charge which was here has moved here. And the charge which was to the right, to the next pixel, has also moved 1/3 of a pixel. And in fact, all the charge on the whole CCD have moved by 1/3 of a pixel to the right. I'm going to do that again and again. And after this process, as you can see, the charge which was in this pixel is now in this pixel. The charge which was in this pixel has now moved to the other pixel, which is no longer in the plot. And here I had an empty pixel here, which arrived right there. So now this is what is being explained here. So here I am moving, let's say, all the charge of this column to the right. So this is coming here, this is coming here, this is coming here, this is coming here. So this is this image now. And now what I'm going to do is, as you can see, the last pixel did not fall in the middle of nowhere. It fell in a special line, which also has pixels, but smaller pixels, which have a way to move in the other direction. So now what we are going to do is the same thing we did to move the whole image one column to the left. We are going to move only this line 1 pixel down. And so this charge is going to go to the sense node, and we are going to read it. And we will know the value of what used to be in the first pixel, in this pixel. We moved here, and then we moved here. We get a signal. And then we are going to move down another time. And so we are going to read this signal. And then we are going to read this signal. And once we will have read these 3 signals, we are going to move again the whole image 1 to the left and read again the 3 signals, and then move again once to the left and read again the three signals. So we are going to read the 9 pixels in order. First this one, then 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 this one. So obviously it takes a lot of time to read the CCD. It's not a good camera to take videos. That's why everybody has a CMOS in his phone to be able to use TikTok. But if you want to make a precise scientific measurement, this is ideal, because the only way you are reading your charge is this place. So if you design this place to be very precise, then you will be able to have a very precise measurement of all the pixels. There is only one place that you have to work hard on. And if you work hard on this place, then you will be able to read the 5 or 10 megapixels with the same precision. So this means that these detectors are great to take pictures, but they are also great as particle detectors. So silicon as particle detector is something we use in accelerators every day. But we are going to use them also to detect dark matter. But what's the idea? Now the idea is, instead of having light, so photons, when you expose your camera to take a picture and having this light converted into charge, we will just not expose the CCD. We will put it in a box so it doesn't get any light. But then when the particles go through the CCD, it's going to interact and create a lot of pairs, like electron hole pairs. And then we will have a strong electric field, which will diffuse these charges inside the CCD until it reaches the pixel. Now, as you can see on this drawing, the charge can go to the pixel where it happened, or to some pixel to the right or to the left. And the reason for that is that the image we have of a pixel, which is something like that, is not exactly the right one. The CCD we are using have pixels by 15 by 15 microns and 675 microns of depth. So in fact, a pixel is something like that. So it's a long spaghetti in some way. It's not a cube at all. And so if your particle interacts here, then you are going to collect all the charge in your pixel, and it's fine. But if it interacts here, you have all the electric field to drift your electrons up to your pixel, but well, maybe it will fall in the neighboring pixel. And so you will have a Gaussian spot, which will have more than 1 pixel of width. So what happens when you expose a CCD to particles? So you don't take picture, you close it, and you just wait for 15 minutes, for example. And here you see an image that we observed on a CCD, and you see a lot of particles. So you see these straight lines, which are muons, so particles will go through your CCD, and you see these kind of worms, which are electrons. So they have a smaller energy, so they are scattered when they cross the CCD. And if you look at them in detail, you will even see that at the end, they have a bright spot, which means they deposit more energy in the last pixels. This is what is called the Bragg peak. Then you have alphas, which have which have plasma effects, and then you have X-rays or low energy, very low energy electrons, which produce these small dots. And if we look for dark matter, what we would expect would be to have some of these very small dots as extra particles in our observation. Now the problem is we want to see very small dots, and the CCD is very precise, but is not as precise as we would like. Basically, when we measure a pixel, the charge of 1 pixel, what we do is we look at what is a zero, and then we put the charge of the pixel and we measure it. And we make the difference between what was a zero and what we observed when we put the charge, and that's the value of the pixel. And just like usually any measurement, we would expect that if we wait longer to make the measurement, we would get a more precise measurement. And actually, it's the case at the beginning, and here you see the precision of the measurements of sigma square and microvolt squared as a function of the integration time, so the time in which we measure both the baseline and the signal. And it goes down, but at some point it starts to flatten, and it even goes up. So this is because there are some noises in 1 over f and 1 over s squared, which are typical from transistors and from the way the electronics work, and there is no way to get rid of these ones. And so what this 1 over f or 1 over f squared mean is that when you integrate your pedestal and then you integrate your signal and you make the difference, if the pedestal doesn't change, then it's fine. The voltage difference you observe is due to the charge. But if the pedestal itself changes a long time, like in this case, then the pedestal you measure during the pedestal measurement is not the one you would have during the signal measurement. And so you have a bias in your measurement, which comes from this low frequency noise. And this is where we, in some way, revolutionized the field almost, well, less than 10 years ago, by introducing the Skipper CCD. So what does the Skipper CCD do? Instead of measuring the charge at the end, it has a floating gate. A floating gate means that it's going to measure the charge we have in a pixel, but not directly, through, let's say, induction in some way, right? So you measure the charge with a capacitor at a distance, and you don't destroy it when you do that. So once you do that, it allows you to, okay, you have some charge here, and you want to measure the next charge. So you just dump the old charge, and then you're putting your new charge to measure, right? So you measure the charge, but then you're removing it, and so you can measure again the baseline. You put it back, you measure the charge, you remove it, you measure the baseline, you put it back, you measure the charge, you remove it, you measure the baseline, you put it back, you remove it, you put it back, etc. So basically, doing that, you are able to get rid of the low frequency noise because you can do that fast enough so that the baseline doesn't change in between these two measurements. It will change between thousands of measurements, but you will be able to follow it. And so while here you had the first measurement in which the pedestal had some value, and then another measurement for the signal in which the pedestal has another value, here we are going to make a lot of measurements, and in each of them we will have pedestal, signal. And so some of them will have a bias, and then some of them will have another bias. And so in the end, the accuracy of our measurement is going to go down as square root of the number of measurements. And it works. So this is the first Skipper CCD measurement in 2017. Here on the right, you have the final image that we took with the Skipper CCD. You have here something like 10 by 10 pixels. And as you can see, the central pixel has one value, which is 1 electron, and all the other pixels have 0 electrons. So in fact, in this portion of the image, there is only 1 electron in this pixel. This image is one of the 4,000 images we used to make this average. So each pixel has been read 4,000 times. And when we make the average, we have this image on the right. But if we look only at one of these 4,000 measurements, we have this image on the left. This image on the left has exactly the same physics as the one on the right. So in this image also, you have exactly 1 electron here and exactly 0 electrons elsewhere. Except, of course, given the readout noise, you cannot see it. And once you make these 4,000 images and average them, then you get the signal to appear from the noise. So this is the histogram of the signal for one readout. And this is histogram of the readout, the signal after 4,000 readout. You can see there is a huge peak at 0. So most of the pixels have no charge. Some pixels have 1 electron. Some have 2. Some have 3, 4, 5, and so on. In addition, since the width of this Gaussian is a readout noise, it does not depend on the signal. So if you have 2000 electrons, then you will still have a peak at 2000, then a peak at 2001, a peak at 2002, a peak at 2003, a peak at 1999, etc. So it's not like you have a multiplication phenomenon like in a phototube or stuff like that. So these are really amazing detectors which allow you to count single electrons in any pixels, knowing if there was or not an electron. So what can a Skipper CCD do? It can move a charge of 1 electron across 10 centimeters, which is more or less the size of the CCD we use, over 24 hours, because a CCD takes time to read, but our Skipper CCDs, we are going to read hundreds of times or even sometimes thousands of times the same pixel. So it will be hundreds of times or thousands of times longer than to read a normal CCD. So these images will take a very long time to read. So actually, in our DAMIC-M experiment, it can take up to 48 hours to read a full CCD. But then, after this, maybe 24 hours to move 1 electron across 10 centimeters of your CCD, you can measure it perfectly, knowing exactly if there was 1 electron or 0 or 3 or whatever in that pixel. And in addition, the dark currents, so the number of electrons that appear in your sensor and are not due to the physics or are not due to interaction from particles, is of about, in the best detectors, of 5 per gram per day. In our detector in DAMIC-M, we are not as good at that. We are at 500 per grams per day. But even that is a very small number, and most other detector technology have rates which are per second. So they hope to be below 10 per second per gram. So we are way lower than that. So now that we've realized we have a fantastic detector, let's try to see what it can do for dark matter. So the first experiment was made in Fermilab, and you can see it's a tabletop experiment. So it has a cryocooler, a vacuum pump, a vacuum chamber, commercial readout electronics. And this is a sensor. It's 250 microns thick, 0.1 gram. This is a few centimeters. This is a quarter of a centimeter, something like that. So these were really, really small sensors. And so with this sensor, they took data there in an office in Fermilab, and they published in PRL 1 year after having the first Skipper CCD image. These limits, which are not really competitive with the big xenon or dark side experiments, but, well, are on the map and are even the best one in some low mass region. But then they decided to make a more serious experiment. So now you see it's a little bit more complex than a tabletop experiment. It has better electronics, it has a better viewer, better setup. And they decided to go to Minos, so underground, 100-meter underground. And a year later, so 2019, again a PRL. This is the limit they obtained. And you see it's still not xenon at high mass, but at low mass is the best one for quite a significant range of energy. And in particular, it's better than CDMS, which was the experiment which was supposed to do all this physics. So, okay, interesting. Now, what next? What can be done? Well, they improved the detectors, and they decided to have so this starts to be a very serious professional detector with a real box, with shielding, with lead shielding, polyethylene, and everything, and to move to SNOWLab. And before that, they made a last measurement with a better Skipper CCD, and this was the last measurement at Minos. And already in 2020, so 3 years after the first image from a Skipper CCD and 1 year after the previous result, they already had a result which was better than xenon, and they had the best result on the full energy scale. It was even now possible to start to put the theoretical model. So the freezing is what I said at the beginning of this presentation. So this is a region where we expect dark matter to be if it was created through the freezing process. So if there was no dark matter after the inflation, so after the Big Bang and after the inflation, if the dark matter is created through this interaction of standard model particles, it has to have a specific coupling factor so that you get the right density today. And so you can do the calculation. It's not too complicated, actually. And you get this line. And it depends on almost nothing. So it doesn't have any free parameters. So if you add some coupling to Z0, you have some changes. But it's a very strong prediction from the models. So it looks like we're getting there. And so all this was Sensei, an experiment at Fermilab. And now I'm going to tell you about DAMIC-M. So DAMIC-M is dark matter in CCDs at Modane. So the DAMIC-M collaboration, of which I am part, collaboration of a few countries. So Argentina is going to disappear very soon, unfortunately, but it's still a collaboration from the US, which may disappear if Trump goes on turning off science in the US, Canada, and then in Europe, so France, Spain, and Switzerland. The experiment is installed at Modane in an underground laboratory in France, 1,750 meters underground. And the idea is just to do what Sensei did, but with a better radioactive environment. So when you do this physics, as long as your detector is not too big, then you can have a measurement where you don't see anything. As long when your detector starts to get bigger, then any radioactivity around your detector will produce you signals. And so you have to be very careful in building a piece which will be in a low radioactive environment. And so we started doing what we call LBC, which is a low background chamber, which is a prototype of DAMIC-M, in order to demonstrate that we can build an experiment with a low enough background so that we can reach the freeze-in and freeze-out regions. So these are some pictures of how we built the detector in Modane, in the underground laboratory, how we installed the CCDs in the box and stuff like that, how we analyze the data at the end. So this is the design of the detector. So you have the CCDs, which are here in the box, and you have some LED, low background LED. Then you have a copper box. Then you have a cryocooler, a vacuum pump. And then you have lead and polyethylene as a shield around it. So this was the theory. This is the real machine. So you see it's quite similar. So this was during the construction. You see pieces of the shield are not finished. Then all this is closed in a shield. And this is a central box in which we have our CCD. So this is a box. When you open the box, you remove the top, you get this structure. So all this is low radioactivity lead. And inside you have a copper box. If you open the copper box, you have two CCDs. So these are quite big CCDs. So this is something like 8 centimeters by 5 centimeters, something like that. Just so it's significant size. Each CCD weighs about 9 grams, so it's a total of 17 grams you have here. And then you put here, you can see the size compared to the hands of the operator in this box, and you close everything. So this was our first result in 2023. Again, physics review letters. You can see here our limit compared to the gray one, which is Sensei, the experiment I've called I've told you about up to now. So DAMIC-M started to be the best experiment, and it was also better than DarkSide and the other experiments, which had slightly improved in the meanwhile, and getting close to the freezing. We weren't as good at low energy because we had quite a noisy detector, and so we decided to study a specific effect that we expect. So at these ranges of mass and cross section, we expect dark matter to interact a bit in the Earth. And actually, we expect a dark matter wind to come to our detector. So the dark matter wind comes from the fact that dark matter is supposed to be isotropic in the galaxy, but we are moving within the galaxy. And so we will have, just like when you move in a car, you get a lot of wind in your face and not wind coming from the back. So it's exactly the same effect. So the sun is moving in the galaxy in the direction of Cygnus. And so this means that we are going to get dark matter wind coming in the reverse direction. So like if dark matter particles were coming from Cygnus, which is due to the fact that we are moving towards it. Then, so during the day, if you have a detector, for example, here in the Southern Hemisphere in Argentina, then you would have dark matter which go through the whole Earth before reaching a detector, while 12 hours later, the detector will be here, and so the dark matter will go directly to the detector and will not cross the Earth. So if dark matter interacts in the Earth, then you would get probably much more signal during the day than during the night, day and night being with respect to this dark matter wind. And so here are a few sites on Earth and how the position of Cygnus is supposed to be. So in the Northern Hemisphere, it goes from right on top of you to just on the horizon. And so we looked at our data, and our data were pretty flat, did not seem to depend on the angle with this dark matter wind, while if it did, then we would expect to have this kind of signal. And so not observing this signal allowed us to say that even in this one electron rate, which was very high that we had, since it was stable, it was not possible to be caused by dark matter. And we obtained this new limit, which was again a PRL the year later, so in 2024, last year. And with that, we had again the best limit on the full space of parameters, but we were still not able to reach the interesting region. The last thing we did was to improve our detector at the low background chamber. So for that, we replaced the two CCD we had by larger CCDs, which are in fact modules of 4 CCDs. Each of them is 6K by 1.5K, so it's about half of the previous one. So that's 13.4 grams instead of 9, let's say, we had before. And we still have 2 modules. So we have 27 grams of CCD. Then in addition, the CCD are higher quality. And we also did a very high-tech improvement, which was to put tape on our detector. So the reason for that is that we realized that, in fact, these boxes were not totally blind. And even if the box itself is dark, you still have photons, infrared photons, which are produced by the shield, which is not cold. I forgot to mention, we have a cryocooler, so we measure with the CCD at 100 Kelvin, so it's cold. It's not very cold, but it's cold. So we don't have a thermal agitation. But the shield around it at 300K radiates infrared, and so these infrared photons can interact in our CCD and produce electrons. And so we solved that by just putting some tapes on our detector. So this was a low-tech improvement. But the result was quite dramatic. So here you can see in blue the histogram of charge we had in the previous science run, and in orange, the current science run. So what do you see? You see a huge bump at 0, then a smaller bump at 1, and then here a few pixels with 2 electrons, while before we had a lot of pixels with 2 electrons and quite a few with 3 electrons. So the game to look for dark matter is to see, well, okay, in the previous science run, I had a few events of 3 electrons, which were probably due to something else, not dark matter, but I had no signal at 4 electrons. So I knew that dark matter cannot produce 4 electrons in my detector. And so this is how I set the limit. But I couldn't say that dark matter could not produce 3 electrons. What I could say is dark matter cannot produce more than, let's say, 10 events of 3 electrons in the CCD I have during the time I observed. Now, as you can see, the improvement is dramatic. And so now I can say that I don't see any events with 3 electrons. I only see events with 2 electrons. And actually, we did something which is a little bit more precise. We figured out that most of these events of 2 electrons were actually due to some defects in our CCD, and that we could ask for, instead of having events of 2 electrons, having events of 2 electrons, which would be 1 electron and then 1 electron on the neighboring pixel. As I said at the beginning, the charge can diffuse into CCD. And so if you look at patterns instead of charge in a single pixel, then we lose maybe half of the events, but we get rid of this noise. And doing this, we analyzed patterns. And out of 141 1-1 pattern expected, we had 144. And then out of something like 0 patterns of the other candidates, we had only 1 event, which is this event, which is 1 pixel with 3 electrons and a neighbor pixel with 1 electron. So this is a huge improvement compared to what we had before. And when we did this analysis and looked at our result, which was a blind analysis, we opened the box and were really stunned to see only 1 event. And with only 1 event, we were able to set these limits, which is this black line. Then depending on the model, it can be this dotted line, but even this black line, which just totally kills the freezing model in a huge portion of the mass of the range of interest. It has been submitted, actually it has been accepted by PRL on last Friday. So it's going to be available in a few weeks. But meanwhile, it is on archive. And so this was really impressive because when we presented these results at the same conference, some experiments were discussing on how to improve their experiment to be able to reach the freezing region. And we have already reached it. And remember, this is with our prototype. And so I told you that I would discuss a lot about detectors and about the Skipper CCD, and I discussed a lot about the technology because I really think it's a fantastic success story. So here are 7 PRL, almost 1 per year since 2017, and there have been other PRL of Skipper CCD doing other things, but it's really impressive to have such a small group of people working with only 1 detector and being able to storm the community on it. And here you can see the evolution of the limit for noble liquid TPC, which are xenon and argon, which are the kings of high mass dark matter searches. The evolution of cryogenic detectors, which were the one which were supposed to do the job we are doing. And our evolution, the evolution of Skipper CCD. So this is our last result where we cross the freezing line. And this is where we are going to be in 2028, normally. We should improve by 2 orders of magnitude our current limit if everything goes according to plan. So the future is today, because actually we are building a DAMIC-M. So we finished the 26 modules that are going to be installed, 350 grams. So this is one of them. And if everything goes well, this is in dashed line the limit we would obtain in 2028 if we don't observe anything. And I hope, of course, we are not going to publish limits, but we are going to have ellipses of signal where we will have a candidate and we will have discovered dark matter in let's say 3 years or so. Here again, you see the freezing line that we will completely kill with our limits. Actually, we are also going to have here with solar reflected, but it's not ready yet. And here in some other models which are freeze out or other theory, where we are also going to kill most of the models up to this 20 MeV, where probably xenon will have to go. And in this plot, you see the neutrino fog. So we are already thinking about what to do when we will reach the sensitivity to see neutrinos. So to conclude, I hope I convinced you that Skipper CCD are unique detectors. They can see single electrons. They have an incredible sub-electron reading noise. They have provided world-leading sensitivity on the full energy scale. They outperform all the other technologies by orders of magnitude. And this is just because, in fact, it's not we are much smarter than the other guys. It's just that our detector is much better. And it's much better because we just took a CCD, which has been an industry standard for 50 years, and we modified a few square microns, something like 70 microns by 20 microns or so, to change the readout system. And by doing this very small change, then we were able to get this single electron, sub-electron reading noise. So once we had that, all the rest of the CCD was already working perfectly because it's the same CCD that has been working for 50 years. And so we benefited a lot of all the technology transfer which had been known for 50 years, and that's why we outperformed all the other technologies so fast with the Skipper CCDs. So our prototype has already excluded freeze-in and the freeze-out parameter space. There are still some parameter space from the theory to explore, and this is what we are going to do with DAMIC-M in the next 3 years. Now, there will also be a lot of new development because the problem with the Skipper CCD is that it takes a lot of time to read them. But it's not a problem if you have no signal or almost no signal, which is what we have in dark matter. But if you want to take pictures of the sky, if you want to have that in a telescope, then it's a problem. And so there are a lot of works which are being done now that Skipper CCD have demonstrated to be so sensitive, such as, for example, multi-amplifier Skipper CCD. So here you have 16 amplifiers, one after another, and you move your chart from one to another one. So it reads as fast as a CCD, and it has a readout noise, which is sub-electron. So actually, these sensors will just replace every CCD in the world. There is no reason to use a CCD if you can use a mass CCD. It's just better. It's just the same technology, but better. Then we could have CMOS Skipper, we could have a C0 CCD, which have a MOSFET instead of a floating end, which is even better. We are thinking about dual phase Skipper to get some timing information when we expose our images. We are using these Skippers not only in Sensei and in DAMIC-M that I discussed, but also in Connie. Carla knows very well this experiment. She's a spokesperson to detect a coherent neutrino scattering. Then there is dark bits and Mosquita to look for milli-charged particles in beam dumps in accelerator physics. Darkness, plan to send a satellite in space. So Skipper CCD are being used in other experiments, and they are considered for the future for Oscura, which would be DAMIC-M but bigger. DESI, so the interferometer for the dark energy survey, is something that is using CCD as of today and is working on upgrading to get mass CCDs. Then if you do few photon interferometry, this is really the best detector you can have. And if you look for exoplanets in space, so for example, HWO, a future observatory in space, it has to use Skipper CCD because this is the only way you can see exoplanets in space. So thanks a lot for listening to this presentation, and I hope to welcome you on board for this amazing trip we are having with our Skipper CCDs.
Thank you, Xavier. Amazing, nice, very nice talk, a very nice result. So I will open for questions. So I don't know if some of you would like to start. Otherwise, we have a lot of questions in YouTube also. Okay, I will start with YouTube then. So we have a question that is regarding the CCDs. How could pattern recognition with artificial intelligence help to identify events? If you can comment on that.
So it kind of depends what you want to do. So in some experiments, we are working on the surface. This is an image from the surface. So for example, in the experiment of Carla Coney, the CCDs are on the surface, and so there is a lot of background from cosmic rays. And so you have to get rid of these cosmic rays. And identifying them also is interesting because, well, if you have an electron or if you have a muon, you don't have the same physics phenomena. So for example, I don't know, the spread of Cherenkov around the particles could be different or things like that. So identifying these kind of particles is something which is really the ideal place to play with artificial intelligence, because this is what it does the best, right? Identifying patterns in images. So this is very efficient to do that. Then for what we are doing in DAMIC, it's not very efficient just because we don't have signal. So I didn't put on my talk an image, but basically a DAMIC image looks like that, except it's 800 pixels by 800 pixels by 500 pixels. So it's 800 pixels by 500 pixels and 1 pixel in the middle with 1 electron, and that's it. So to analyze these kind of images, you just don't need artificial intelligence. The images are so empty that we actually don't use it. So the analysis is a bit more complex because there are some sources of noise that we get rid of, but these images are so clean that we don't really need artificial intelligence to do these analysis and to find this event, which is just a boring 2 pixel out of nothing around it. But for experiments which are with a higher background, so experiments which are at the surface like Coney, or experiments which are doing beam dump, then you may have significant background that you want to remove. And for that, pattern analysis from artificial intelligence is a very good method.
Thank you. Another question is about DAMIC-M. Is a DAMIC-M capable to detect the sub-electron charge? What are the implications of this?
So in DAMIC-M, as you can see, I mean, sub-electron, is it about the resolution? If it is, then here you can see that actually our resolution is good, but not perfect, right? So for example, if I have one event here, I cannot know if it's a 0 electron pixel or 1 electron pixel. So the reason we could measure our image with a resolution enough to separate these two Gaussians, and so we would not have this issue. But to do that, it would take more time to read the image. And so if it takes more time, then we would have more electrons which come from these 5 electrons that I said somewhere. 5 electrons per gram per day. In DAMIC, we have 500 electrons per gram per day. So right now we are reading our images every 9 minutes. But if we took probably an hour, which is what we would need to be able to separate perfectly these 2 peaks, then we would be able to separate the 2, but the one would be higher, would have more electrons. And having more electrons is not really a problem, but we would also have more double electrons, would have more chance of having a random electron by the side of an interesting event. And so all our physics range would be worse. So we have optimized our timing, our data taking conditions to have the best sensitivity possible. And so this implies that we don't have perfect sub-electron capability. Our readout noise is about 0.2 electron. So that's much better than any camera. The Vera Rubin cameras have 6 electrons or 5 electrons. of readout noise. We have 0.2 electron, so it's incredibly better than any CCD on Earth. But it's not the best we can do, because if we improve the quality of our measurement, the physics get worse because we have more background.
Yes. So regarding background, I have two questions. One that is in YouTube and another that it comes from me that is maybe they are connected, so I will do both at the same time. One is you showed that your limit in the background single electron is 5 electron per gram per day. So my question is, what is limiting you to reach the limit on the dark current emission? And then there's here two questions that are regarding background characterization and the radiogenic natural activity, and which are the primary background source. So if you can comment in background more, it would be very nice.
Okay, so first, so right now we are at 500 electrons per gram per day for just the DC, so the dark current. And we know we can do better. First, because our colleagues at Sensei are at 5 electrons per gram per day, so we can do better. It's more or less the same detectors. But also because when we turn on a light in our box, when we measure pressure, there is a pressure gauge which emits light, we increase our DC. So we know that even with our tape to tape the holes, we did not do a perfect job. There is still light entering in our detector, so we know we can improve that. In the DAMIC-M design, the CCD box are much better, are tight, and there are systems to not get a direct exposure from the shield. So we should not have this issue. So we should improve our DC for the future. Then on the radiogenic background, actually we expected 0.07 event, and we had 1, which we believe is from radiogenic background. It's also due to the fact that we did not close totally our shield. It has a small gap of 5 centimeters. The reason for that is that when we closed it totally, we had some electronic noise in the readout, so we opened it, it worked. And since we didn't think, I mean, it's our prototype, we were not thinking we would have a fantastic science result with that. We said, okay, that's it, and we left. And we took data, and we took a week of data. And we said, well, we are going to do a modulation measurement to show that our detector, that with the tape, will reduce the DC. And we looked at the images, and they were so good, we decided to take a second week of data. It was so good, we decided to take 2 months of data as a blind data, opened the box, found this result, and killed the freeze in and freeze out. It was not what we expected. And then we had to argue with the reviewer explaining why we had left 5 centimeters open our shield. Anyway, so even with these 5 centimeters open of shield, we were expecting only 0.07 event from radiogenic background. Now for DAMIC-M, this is too much, since we expect to have a factor of 100 in exposure, and we will probably have a lower DC, then we already have 1 background event, probably because we were unlucky. We were expecting 0.07, but still, if we multiply that by 100, it's still of the order of 10 events or something like that, so it's not good enough. So we are improving our shield quite a lot. So all the lead, which is close to the detector, which was this lead, so it's not the same. We have 26 modules in the final design, so the design is totally different. I should have added 1 slide on it. But still, there is some lead shield close to the detector. So this lead shield is not low radioactivity lead as the one we have here, but archaeological lead. So archaeological lead is lead that have spent thousands of years underwater. Actually, it's so it's a boat which was found a few tens of years ago in the Mediterranean Sea, which had spent 2,000 years underwater, and so for 2,000 years, all the lead which was in this boat could decay. So the 22 years of lead-210 has decayed, and we take this lead, and this is the one we use to do the background around our detector. In addition to that, we have some the copper pieces here, will be replaced by what we call electroformed copper. So this is copper that we produce atom by atom, so that there is no impurity, so that you don't get any other radioactive signals. So copper is fantastic. It has no radioactive isotopes with a lifetime of a few hours. So it's fantastic. It's extremely radio pure, but there are impurities, and if it's exposed to cosmic rays, also there are impurities. So we get rid of that. The silicon themselves from the CCDs that we've constructed, I think it was at the end. Yeah, here. So all these CCDs which were built and tested have been exposed to cosmic rays less than a month from the time they were constructed to the time they have arrived to Modane. So this means that every time we were testing them or doing anything, not testing them, they had to be in a lead castle in a container to be protected from cosmic ray activation. So all these efforts, we also have low radioactivity cables and etc., etc. So all these efforts allow us to believe, at least Monte Carlo, we are understanding the background we have at LBC with the Monte Carlo. We have the correct rate of event at high energy from the Monte Carlo. So we expect that we will reach this 0.6 DRU we expect to have for the final detector with this archaeological lead, electroformed copper, and that's it.
Thank you. Very complete answer. Other questions from the audience? Okay, if not, I will
No,
go ahead, Roberto.
Yes. Javier, very nice. Very impressive also the results from the DAMIC. So I have a question, just kind of when you were talking about the future. What is the reason why there is this lower mass threshold for the dark matter? I mean, for the exclusion, is a technological level that is not possible to go? Do you have the pump at the low mass level, or it's just a kind of
So,
I mean, because of the halo of the dark matter or something like that? I mean,
no, at low mass, it's just the fact that you need your dark matter to leave a signal in your detector, which is higher than the minimum signal you can observe. So this means that if you are below 0.6 MeV, you cannot kinetically produce 1 electron in silicon, which is 1.2 electron volt. So this is our lower limit. And then as long as you have only 1 electron of signal, there is no way for you to distinguish 1 electron from dark matter from a 1 electron from something else. So the only limit you can set is saying that all the things you see are coming from dark matter. So this is not a very strong limit, except for modulation. But then when we reach these cross sections, Earth is transparent, so you don't have modulation anymore. The thing you can do at low energy is what you see this line here, which says solar reflected, and it's here also, solar reflected. So this is that even, I mean, at these energies, at these cross sections, what you can have is dark matter which interacts in the sun. And if dark matter interacts in the sun, it's the opposite of what happens in the Earth. If dark matter interacts in the Earth, it is slowed, and so you will get less signal. If it interacts in the sun, of course, the electrons or the nuclei there are at very high energy, and so it is boosted. And so the spectrum of dark matter is boosted to very high kinetic energies. And so you are able to see them in a detector because of this boost of kinetic energy, which now allows for this low mass dark matter to create 1 or 2 electrons or 3 electrons or 5 electrons in your detector. And so these solar reflected bands are something we are working as of today. I hope that within a few months we will have a result with our current data set. And with DAMIC-M, we'll have results. So I don't know if we can get up to 10 to the minus 38, or if at this level the sun becomes transparent and we don't have the capability to reach that. I don't know. I should look at that. But this is the only way with our detector where we could reach this low mass region. If you want to go to low mass, then you need a lower mass atom or lower band gap than the silicon. For that, for example, Tesseract, at least the helium version of Tesseract, is a good candidate. And then you have all these new material technologies where you design your material by yourself. So you put different atoms one by side of the other one, so that the interaction of the different atoms make the last electron to be attracted, and so to have a very low coupling to your atom. And so by doing all this magic nanotechnology, you can create materials with a band gap that you wish. So you can construct the band gap you want. So you could have a very low band gap to be able to measure KeV dark matter. The problem is you have to create it atom by atom. This is nanotechnology, and so nanotechnology is not the best way to have grams or kilograms of detector. So it's, I mean, there are ideas on how to do things like that, but there is no real detector as of today.
Thank you.
Hey,
Any
thank
other
you.
question? Okay, if not, I will finish with the last one that is in YouTube. That is, would it be possible to put DAMIC-M near a nuclear reactor facility to look for axion-like particles? I'm interested in this answer. That's why I'm doing it.
Yes. I will argue about putting Sensei close to a reactor. So now that we are entering into DAMIC-M, so unless we have a catastrophic failure, then DAMIC-M will reach sensitivities which are beyond any other experiment, and no experiment will be able to reach the DAMIC-M sensibilities in the next 5 years. So it doesn't make a lot of sense to keep measuring with Sensei, for example, for searching for dark matter. And so Sensei is still a very good experiment. It's still a big experiment. And so it would be very nice to have Sensei moved to a different target. So one option is to move it to a beam dump to do MCP. So you would have to move it to an accelerator. It could be in the US, or it could be in Europe, or you could move it close to a nuclear reactor, also to look for more than actions or action-like particles, to look also for midi-charged particles. So also kind of dark matter which couples to the electron, but very weakly, so that it gives you the interaction equivalent of an electron which would have a fraction of its charge. So this is something which is very interesting. Then DAMIC-M itself in 2028, it will probably have to be dismantled. So at that moment, it will still be the most sensitive detector on Earth. It will be a big camera, so it's 1 gigapixel camera, so it's a third of a Vera Rubin. So it's really a big detector. It's a really big camera. It just doesn't take interesting picture compared to Vera Rubin. But it's really a big camera. It's almost it's one of the biggest. It's the third biggest camera. It will be the third biggest camera in the world. So moving DAMIC-M close to a reactor, probably. I mean, in France we have a lot of nuclear reactors. Could really be a good plan. Or moving it to CERN. That's also a possibility.
Okay. Okay, great. Thanks a lot. Now we are more than an hour, so thanks a lot for the presentation, for coming. Keep tuned because the sensors are very nice. So I would say I'm a little biased, but okay. Thanks, Xavier. See you now. Since I'm new, I'm not sure, but we will enter in a break for the winter summer holidays, depending on the hemisphere where we are, and we will come back in September. So we will announce that, right? Okay, so see you in September. Have a nice holidays then, and thanks again, Xavier, for coming. Bye bye.
Thank you for the invitation. Bye bye.
Okay, we are out.